Hey everyone, in this video I'm going to talk about how to select electrical components, specifically capacitors. Alright, so first off, what is a capacitor? It's a device that has a well-defined relation between charge and voltage. So you put more charge in the capacitor, you get more voltage. You're going to use capacitors in your circuit to have a small energy source local to wherever you're consuming that energy. What does that look like? Well, anytime you have an integrated circuit, you're going to want to put a small decoupling capacitor, something like 1 nanofarad, maybe 10 nanofarads. If it's a really big, heavy load, you might put a 1 microfarad decoupling capacitor. So that's where you use really small capacitors. On the other side, using big capacitors, typically you'll need those on the input of power converters because you need to reduce the local impedance, and a capacitor is really good at doing that. Alright, so let's say you actually want to choose a capacitor. What are the things that you care about? Small capacitors for decoupling, you're pretty much guaranteed to use a ceramic multi-layer capacitor, an MLCC. These look like just little boxes. First off, what package are you going to use? Well, you have the choice of... The big choice is through-hole versus surface mount. Now, a through-hole capacitor looks like this. A surface mount capacitor looks like this. And yes, the surface mount capacitor is much smaller. Through-hole components are much easier to install by hand. It does take a lot more finesse to solder down surface mount components. It is quite doable once you get practice, but not nearly as easy as through-hole components. The big advantage to surface mount components is that they take up way less space. A 1 nanofarad capacitor really does not need a whole lot of volume. But the package for a through-hole 1 nanofarad capacitor is going to be fairly large, and that's mostly due to lead spacing for through-hole components. Surface mount components, they're just generally much more compact. Personally, I recommend using surface mount components for decoupling capacitors. It's just going to perform literally better because it's smaller. So now you've chosen a package, what are the other things you need to know? A ceramic capacitor has something called a temperature coefficient. As you change the temperature away from room temperature, you're going to start seeing a reduction in capacitance. If you get an NP0 or C0G capacitor, that is a temperature coefficient that is nearly invariant across its temperature range. If you really care about your capacitor having a stable value across temperature, you are going to get the NP0 or C0G. If you don't care that much about the value, for instance, most decoupling capacitors, it doesn't matter if you change a few percent or even a few tens of percent. You can get the next best coefficient, which is X7R. That is extremely common, it's actually going to be cheaper, and you can get larger values of capacitance in the same volume of package. Something else you need to know about ceramic capacitors is that the value of capacitance will change as you apply a DC voltage. So let's say you have a 10 volt rated capacitor and it's rated for 1 microfarad. Well, at very small voltages you will see that 1 microfarad, but if you charge it all the way up to 10 volts, you're not going to see 1 microfarad. You might see all the way down as low as 0.2 microfarads. What does this mean practically? Well, it means that you need to have lots of margin on your voltage rating, or lots of margin on your capacitance rating. One or the other, or both. So let's say you've decided to go with ceramic capacitors, but maybe you want to start storing a little more energy. Maybe you're talking about the capacitor bank on the input of your power converter, or the output capacitor. You can build up several tens of microfarads by just putting lots of capacitors in parallel. You can do that. And as you start selecting larger and larger values of capacitor, you're going to start seeing the package size go up. So you might see, for example, a large case is 2220. Compare that with a smaller case of 0603, 0805. Those are really common packages. Ceramic components generally, and this includes ceramic capacitors, the larger you make the component, the more likely it is to crack. That's because thermal stress in a component gets worse the larger the component is. So if you want to make a small ceramic part, it's easy, it's cheap, it's reliable. As you start making larger and larger ceramic parts, you're more likely to just see catastrophic failure. If you have your capacitor bank charged up to full voltage, and then one of those capacitors decides to crack, you're going to see a catastrophic failure most likely. If you do want to use larger ceramic capacitors, you can mitigate the effects of stress by using packages that are called J-lead packages. This means that the component is not soldered directly down onto the board. Instead, the component is attached to these extra terminals, and these terminals have just a little bit of flex to them. That little bit of flex can mitigate that thermal stress. It sort of mechanically decouples the capacitor from the board you're soldering it onto. You can build up a few hundred microfarads of capacitors using ceramic capacitors, but it will be much more expensive than using other types of capacitors. Ceramic capacitors are very good if you want to send stuff to space, because they tend to work well over a wide temperature range. You can very easily get ceramic capacitors that operate down to minus 40 C all the way up to plus 150 C. That's no problem for a ceramic capacitor. For other types of capacitor, that can be a challenge. Alright, the next type of capacitor is aluminum electrolytic capacitors, and these things are very good for lots of capacitance value for the money. They are very cheap. The downside is they tend to have a large ESR, equivalent series resistance. Ceramic tends to be very low in that regard, which is good. Aluminum electrolytic capacitors, they tend to have quite a bit of resistance. That means if you're putting a large ripple current through your capacitor, an electrolytic capacitor is going to heat up more. Electrolytic capacitors, they don't really like temperature extremes. They don't really like going much below freezing. They don't really like going much above 100 C. And if you operate them in those ranges, you will increase the wear and tear on them significantly. Just keep in mind, if you have something that's operating here on Earth, if you're operating in a reasonable temperature range, so you're not freezing it, you're not taking it over 100 C, aluminum electrolytic capacitors can be a fantastic choice. They can save you a lot of money. As far as the packaging on electrolytic capacitors, you don't actually save that much space going with surface mount versus through-hole. So if you are installing these by hand, through-hole capacitor can be a fantastic choice. They are available in surface mount packages. They look kind of like this. Use whichever one works best with your design. To my knowledge, there is not really a DC bias effect in electrolytic capacitors. If you have a capacitor rated 100 volts and 100 microfarads, if you charge it up to 100 volts, to my understanding, you will still get pretty much 100 microfarads. That DC bias derating is really in effect for ceramic capacitors. What are going to be the limitations on a capacitor that you select? Well, the big one is going to be you have to select capacitance value, whatever value you want, whether it's 1 microfarad or 10 microfarads or 1 nanofarad. That's the first thing you're going to choose. You're also going to choose a tolerance on that. You can easily find tolerance down to 1% if you want a really precise value. And you can get all the way up to 10 or maybe 15% tolerance on a cheaper capacitor. Another type of capacitor I'll mention just briefly is something called a film capacitor. These tend to work well over temperature range, better than electrolytic. These are generally good if you want to have a larger value capacitance, but an electrolytic capacitor just won't do it for you. If you need larger value capacitors, so we're talking tens or maybe 100 microfarads, but you can't quite fit it with ceramic and maybe your temperature range doesn't work with electrolytic, choose a film capacitor. These are kind of an in-between technology. A note on capacitor data sheets, they really run the gamut in terms of quality. Some capacitor data sheets will not tell you pretty much anything other than the dimensions, if that. Quite often a capacitor data sheet will actually have hundreds of part numbers that it covers. Usually capacitor data sheets cover a family. They don't cover a single part number. And if you dig through it, you'll find a lot of information, and some of it might be what you need. Some of it might not. So here's a tip, especially for ceramic capacitors. If you take that part number and you go to the manufacturer's website and you plug in that part number, you will usually find an interactive data sheet that gives you all of the information you might want to know about that capacitor. This is more common for the big, good manufacturers. If you're buying from some small, no-name brand, you just won't find this information. But a big name like Kemet or Murata, you're probably going to find this. Alright, so this has been kind of a quick and wild overview of capacitors. It's certainly not comprehensive, but I hope this has given you enough information to be dangerous as you're selecting capacitors. The big thing I want to get across is that for small value capacitors, you really have no need to choose a through-hole component. Surface mount is really going to be best for small MLCCs. If you need more capacitance for the money, electrolytics are a great budget option. And if you need a little wider temperature range and you still need large value capacitors, film is a great choice. Alright, so thanks for watching. I hope this has been educational, I hope it's interesting, and I hope that after watching this video, you're a little bit better prepared to select a capacitor for your design. My name is Colby, I'm a power supply designer. Thanks for watching. Bye-bye.